This tutorial will show the powerful tools that the SAP 2000 Bridge module offers for the automated seismic design of bridges. Following the procedures described in the AASHTO Seismic Guide specifications, SAP 2000 can automatically calculate demand capacity ratios, including those for seismic design Category D bridges, and can produce a report containing all design results. The seismic design of bridges using SAP 2000 consists of 8 basic steps. A quick overview of these 8 steps is as follows. In step 1, we construct the model using bridge objects. The focus of the seismic design is on the bents. These bents will be isolated by the program when doing a pushover analysis. In step 2, we determine the ground motion hazard. This can be done by simply giving the bridge coordinates using latitude and longitude or zip codes. In step 3, the program applies the dead load to the entire bridge and calculates the crack section properties of the columns. In step 4, the program calculates the modes, performs response spectra analyses, which then gives the demand displacement values. If the bridge is a seismic design Category D structure, the bents and foundations are modeled with equivalent loads in step 5. In step 6, the program calculates the displacement capacity. Code equations are used for seismic design categories B and C, and a pushover analysis is performed for Category D. In step 7, the program calculates the demand capacity ratios, and in step 8, a seismic design report is produced. Now let's take a closer look at each of these steps. Step 1, building the model. Our model has 3 spans of approximately 60 feet, consisting of an 8.5-inch slab supported with 5 3 feet 3-inch deep precast concrete girders. 2 bents, each with 3 36-inch diameter columns 26.5 feet tall. These columns could have been fixed at their base, but for our model we are including a foundation consisting of a 4-foot thick pile cap supported by 14-inch diameter concrete piles with steel casing. Because seismic design is automated, the bulk of the work for the user is in building the bridge model. However, building a model is described extensively in other watch and learns, so we will go through this first step rather rapidly. Here's how we built the model. We started by going to the Bridge Information Modeler wizard. The wizard guides you through the modeling procedure. The first item is the layout line. Double-clicking shows that we have one line defined. The line provides the coordinate stations for the bridge. Our model has 2 stations, an initial station and an end station 178.42 feet away. For materials, we will use the 4000 psi concrete and the A615 grade 60 for the reinforcing steel. Check the Show Advanced Properties option so that we can review the nonlinear settings for these materials. Next on the list is the frame sections. The cap beam, the column, the precast eye girder, and the pile. The BRD sections shown on the list are equivalent frame sections created by the program to represent the combined behavior of the deck plus the precast girders when doing a spline model. The cap beam is a rectangular section 39 inches deep by 42 inches wide. The bent column section was created using the section designer. A right click shows that the section is 3 feet in diameter with 13 number 8 bars for longitudinal reinforcing and number 4 spiral confinement. The girder was created using the precast concrete I-girder form. Note that it is 39 inches deep and 13 inches wide at the top. The last frame section created by us was the pile. We created a round concrete section with a 14-inch diameter. However, the pile has a steel casing, so to account for this, we assign property modifiers to increase the moment of inertias. Now we move on to the bridge component properties. Double-click on the deck section. We have a single deck defined with 3 interior girders and 2 exterior girders, which gives us a total of 5 girders. The girder section is the precast section just discussed. The deck has a width of 38 feet 10 inches and a slab thickness of 8.5 inches. The program takes this complicated cross section and converts it into a single BRD frame section for use when doing spline models. The next item to review is the bearings. We have 2 different bearings. The first bearing is for use at the abutments and restrains motion in the vertical direction. The second bearing is used at the bents and restrains translation in all 3 directions. Next is the foundation spring. We have defined one spring property to be used at the bottom of the bent columns. In this case, all releases are set to free, as we want the forces from the columns to be transferred directly into the pile cap foundation. If we were not explicitly modeling the foundations, we would set some or all of these releases to fixed. For the abutments, we have a single type that provides a fixed connection to the bottom of the girders. We have defined a single bent for both locations. The bent consists of 3 columns topped with the cap beam we defined. The columns are 26.5 feet tall and use the previously defined foundation springs for the base support. At the top of the columns, all connections are fixed to the cap beam. Next is the bridge object definition. The bridge object tells SAP 2000 how to assemble the previously defined components into a bridge system. The bridge object assignments allow SAP 2000 to isolate the loads and the bents that are used when doing the automated seismic analysis. For this model, we have a single bridge object that contains all of the components for our 3-span bridge. The reference line for the bridge defines the abutment and bent locations. Selecting spans and clicking the Show button, we see that the deck section is assigned to each span with no variation. The start and end abutments are the same. A 2-inch thick bearing resting on our fixed substructure. The bent assignments for each span are also identical. Again, a 2-inch bearing resting on our bent structure. After doing the assignments, it is important to link the model so that all components are included in the model. Our superstructure is complete. The only item we did not review in the Bridge Wizard was the foundation. The foundation consists of a 4-foot thick area object for the pile cap, supported by the pile objects. Note how the bottom of the column is above the area object that represents the pile cap. If we extrude the objects, we can see that this is geometrically correct due to the thickness of the pile cap, but because the pile cap was modeled with a planar object, we use a weld constraint to connect the bottom of the column to the center of the planar pile cap. For this model, the only static loads we will apply will be the dead and superimposed dead needed for the seismic analysis. We are now ready for Step 2. Step 2 is where we determine the ground hazard. We go to the Define, Functions, Response Spectrum command, and here we have many choices for response spectra functions. We will choose the National Cooperative Highway Research Program spectra. Function values may be determined by the program from latitude, longitude, by zip code, or by user input. We will input latitude and longitude. Note how the spectra values change based on the input. We will set the site class to D. With the determination of the site hazard, we are just about ready to start the automated seismic design. The last bit of information that we must input is the design request. This tells the program what type of seismic design to do. Go to the Design, Bridge Design, Define Seismic Design Request command, and click on the Add New Request button. Note that the bridge object we defined is selected, as our model has only one bridge object. Click the Modify Show button and review the options set by the program. Note that the EQ function is selected, that the seismic design category is set to D, so a pushover analysis will be done. Also note that the entire structure is being used for the gravity load case. The crack sections will be determined by the program, and that the modal load case will be program determined. Lastly, we need to identify the foundation group because we did not fix the columns at the base. Just to reiterate, the only load cases defined at this time are for the dead loads. We will return to this form after running the seismic design. The program will automatically create load cases for all of the other analyses that will be done, including modal and pushover. Now, we will start the automated seismic design procedure, which will do steps 3 through 7. This may take some time as a large number of different analyses are being done by the program. Now that the analyses are complete, we can scroll through the analysis window to see exactly what the program was doing. First, it applies a dead load to the entire structure and iterates to determine the crack section properties. Based on the crack sections, it performs a modal analysis, with these modes, it performs 3 different response spectrum analyses. Next, it performs a dead load analysis using just the bents and equivalent loads. And lastly, it performs 4 different pushover analyses. Next, we will return to the load case form for a more detailed look at the automated analyses. Note all of the additional load cases that have been generated by the program. The first one represents the results of step 3, the application of dead load and the calculation of the crack section properties. Dead load is applied to the entire structure along with the section modifiers. This load case represents an iterative process when calculating the crack sections. Element forces are determined, crack sections are calculated, stiffnesses are modified, and the cycle is repeated until convergence is reached. The actual cracked section modifiers used may be reviewed by going to the Define Name Property Sets Frame Modifiers command. Here we see for bent 1 column 3 the moments of inertia are multiplied by approximately 0.28. The next four cases represent step 4, mode extraction, and then response spectrum analysis to calculate the demand values. Note that the modal case uses the gravity deadload case with the cracked sections as the starting stiffness. For this bridge, the program asks for 18 eigenvectors. The number of modes is determined by the equation 12 plus 6 times the number of spans minus 2, but no less than 12. Here are some of the modes calculated by the program. The next case is the response spectrum case in the x direction. Modal damping of 5% is used. The following case is the response spectrum analysis in the y direction. And the last case applies the response spectra in both directions and combines them according to the AASHTO seismic guide specifications that require results to be combined using the 130% rule in each of the major directions. The next case is associated with step 5, and again represents a dead load case. But this time consists of only the bents and foundation structure loaded with equivalent loads from the bridge deck. Again, cracked sections are used. This step is needed because the structure is seismic design category D, which means a pushover of the bents is required. Prior to step 5, hinge properties are calculated for the pushover analysis. The automated seismic design request uses hinge properties based on the AASHTO Caltrans idealized model. Note that the program uses PMM hinges, so properties are dependent on axial force, which varies as the bents are pushed. Because the seismic design category is D, the program automatically performs a pushover analysis on the bents that are part of the earthquake resisting system. The last four load cases are associated with step 6 and represent pushover analyses in two directions on each of the two bents. The first case pushes bent 1 in the transverse direction. Note that the pushover starts from the gravity case for the bents. The program automatically sets all of the parameters. The next load case is the pushover on bent 1 in the longitudinal direction. The third pushover case is for the second bent in the transverse direction, and the last pushover case pushes the second bent in the longitudinal direction. From the pushover analysis, the program determines the displacement capacity. Going to the Display Show Static Pushover Curve command, we can view the pushover curves for each of our 4 pushover cases. Typically, the displacement capacity is taken as the point on the curve that is located just past the peak base shear location, where the base shear is 99% of its peak value. Once the pushover analyses are complete and the capacity displacement has been calculated, the program automatically generates the demand-capacity ratios, which can be viewed by going to the Display Show Tables command and selecting the Bent Demand Capacity AASHTO LRFD 2007 table. Here, for each bent and each direction, the table reports the demand, the capacity, and the ratios. The last step is to generate a seismic design report. The program will generate a comprehensive report with a single click. Go to the Design, Bridge Design, Create Seismic Design Report command. The report includes a complete table of contents, images of the model, bridge data, section properties, loads, and all design results. Revisions may be done directly by the user. This concludes this tutorial on automated seismic bridge design.